We have a paradox in AI development. Frontier models are remarkably capable in single-turn reasoning, but they consistently fail when deployed in long-horizon autonomous workflows. This isn't a lack of reasoning power, it's a problem of probability. Consider a pipeline where an agent succeeds 95% of the time at each step. Across 20 decisions, errors compound. The end-to-end completion rate plummets to 36%. This drop-off is a structural failure of probability. It persists even as models get smarter, because no matter how high the reasoning capability, the math of a 20-step sequence remains the same. Entrusting a naked language model with complex autonomous tasks is mathematically unsustainable. To bridge the gap between a 36% success rate and production-grade reliability, the model requires a rigid structural intervention. Between 2022 and 2024, we relied on prompt engineering, optimizing phrasing. By 2025, focus shifted to context engineering, improving the information supply provided to the model. Now, we move toward harness engineering. The goal is architecting the execution environment itself. To solve for the probability decay we saw earlier, developers are adopting a new framework. The agent is defined as the model plus the harness. In this model, the LLM is the engine of raw probability, while the harness acts as the deterministic chassis, the telemetry, and the braking system required to steer that power toward a specific result. The highest leverage activity in AI development has moved. It is no longer about engineering the model's output, but rigidly engineering the environment in which that model operates. An effective harness relies on 6 pillars. The first is the context firewall. Dumping entire codebases into context windows degrades reasoning. We use progressive disclosure, supplying minimal tool signatures initially and injecting documentation strictly at execution. The second pillar is tool sandboxing. There is a common assumption that giving AI more tools makes it a more capable agent. Vercel tested this by supplying an agent with a massive tool library. Instead of becoming more effective, the agent hallucinated complex workflows and made redundant API calls. Their solution was counterintuitive. They cut the agent's toolset by 80%. This massive restriction in choices led to higher task completion rates and significantly lower token spend. For the tools that remain, teams like Stripe use the DevBox methodology. DevBox forces agents to execute in pre-warmed, fully isolated environments that are identical to human workspaces, strictly cut off from production systems. This is the constraint paradox. Artificially restricting the environment and limiting the agent's choices is the only proven way to increase its autonomous reliability. Pillar 3 is verification constraints. Anthropic and DeepMind both utilize a tripartite architecture. Work cycles through a planner, a generator, and an evaluator. This solves a fatal flaw in agent design, allowing an LLM to evaluate its own work. Models exhibit a structural bias. They are overconfident, often grading their own subpar outputs as successful. To break this loop, the evaluator must be an entirely independent agent, or ideally, a hard deterministic linter. You apply hard constraints like pre-commit hooks and structural tests that do not rely on LLM reasoning at all. Physically decoupling the generation of code from the evaluation of code is the only way to stop an agent from hallucinating its own progress. Pillar 4 is state persistence. LLMs are amnesic across long horizons. We solve this by externalizing memory, writing to durable artifacts like JSON to-do lists and Git commits, creating rollback checkpoints. Pillar 5 is observability and systemic entropy. To see how these modules work at scale, consider a recent keynote presentation in London regarding internal projects at OpenAI. A team of only 7 engineers generated 1 million lines of code and 1,500 merged PRs using agents. That level of velocity creates massive, rapid entropy. Slop accumulates in the codebase faster than a human team can track it. OpenAI's solution is continuous garbage collection. They use background daemon agents whose only job is to scan the codebase for inconsistencies and refactor them automatically. Combating entropy is a mandatory observability practice. It ensures the environment remains legible so that future agents can operate without getting confused by old errors. The final pillar is the human handoff. Autonomy requires boundaries. You must embed hard, deterministic stops within the harness for any high-risk, irreversible action. Executing financial payments, dropping database tables, or sending communications must trigger a pause for human confirmation. The goal of harness engineering is to build a structured, capable copilot, avoiding the risks of an unconstrained autopilot. By applying these 6 pillars, we solve the math of compounding failure. We turn the 36% success rate into a production-grade system. Frontier LLMs are rapidly converging in capability. As raw reasoning scores stabilize, models are becoming a commodity. The performance gap is no longer in the weights. The technical moat is the robustness of the execution harness built around them. This shifts the role of the software engineer. The job is moving from writing implementation code to defining the architectural constraints and verifiers that govern autonomous action. Mastering this architecture is what separates fragile local AI experiments from production-grade autonomous systems. Relying on raw model intelligence alone is a mathematical trap. Stop trying to write the perfect omnipotent prompt. Start architecting the perfect constrained environment. Smart, rigid environments are what turn probabilistic models